Okay, so it's 11 a.m., so it's time to continue with the next presentation by Professor Martin Savage. My name is Cristian Batista, and I will be chairing this presentation. So Martin got his PhD at Caltech in 1990 and became a postdoc at Rutgers and UC San Diego, eventually landing at the University of Washington, where he is now a professor and senior fellow of the Institute of Nuclear Theory. He's also a fellow of the American Physical Society, and he has made important contributions to learning and applying quantum computing and quantum information theory to grand challenge problems in nuclear physics. The classical computing resources required for precise QCD lattice predictions in finite density systems and in non-equilibrium systems and in fragmentation are estimated to be beyond exascale due to sign problem in sampling path integral and due to calculations being performed in Euclidean space. Martin developed and applied lattice QCD techniques to perform calculations of light nuclei on few baryon systems whose precision is limited by the available computational resources. So quantum computing offers the possibility of computing finite density systems in Minkowski space and with high precision. So with increasing access to quantum devices, he is developing algorithms for quantum field theories and nuclear effective field theories to solve these systems on quantum computers. So Martin, the virtual floor is yours.
Thank you very much for that lovely introduction. It's a pleasure to be here speaking to you. We're living in this very interesting period. It doesn't come along very often, where we're seeing really two new computing technologies and techniques enter our field, into nuclear physics. One is machine learning, and the other is quantum computing and simulation. So I know a little bit about quantum computing, and I know less about machine learning. They're both changing and going to continue to change how we compute, how we deal with large systems, and how we make predictions of importance to nuclear physics and supporting the experimental program and ultimately reaching our objectives. How I got into this was through, as Christian mentioned, through the lattice QCD calculations and being involved in, as many of you were, in understanding the exascale classical computing requirements to address the key challenges in our field. And there was underlying themes and underlying features of the systems that were going to require beyond exascale computing. And so this coincided with the time period where national labs were spinning up and technology companies were starting to first, so this is IBM, was starting to first make simple quantum devices available and cloud accessible for scientists. And so this coincided, these two events coincided within the space of about a year of each other, which worked out well. So, and then subsequently in 2019 was really a banner year. It's 2019, we saw the first demonstration of a quantum advantage of any quantum computation, sorry. And so Google announced that with its 54 qubit chip, its superconducting chip, that it demonstrated a quantum advantage in being able to perform a computation in minutes that would take classical computer days to do. Of course, this wasn't a standalone activity. This built upon decades of advances in engineering and controlling entanglement and coherence in the lab, from technology companies, national laboratories, and universities working closely and loosely together. So this is one of a number of architectures that are being pursued, and one, I think we're all fully aware of what the different architectures are, and I'm going to talk about those a little bit more as we go on. So this was a remarkable accomplishment. However, it was not really alone, isolated to the superconducting technologies. There are, for instance, an analog simulation and annealing, as we saw from our previous speaker. And in hybrid technologies, there's advances that are basically at the same level and moving at the same rate. So, so you heard about annealing from, as I said, from a previous speaker. In cold atoms and trapped ion systems, there's comparable advances. Here I show a display from 53 trapped ion qubits, a two-dimensional array that was implementing spin-dependent interaction of the form of, as shown here in this Hamiltonian. It was able to look at the phases of magnetic systems, look at correlation functions with individual ion control, and essentially near perfect measurements. So the number of devices in 2017, the number of devices was quite limited that we have access to. The situation is quite different today. So we have access to superconducting technologies, for instance, IBM Rigetti. There's the D-Wave, as mentioned previous, trapped ion systems, Rydberg systems, cold atom analog simulation. And the architectures have different properties, they have different features. And for the problems that we have, while some may be, some of these architectures may be better suited to some of the problems in general, we don't understand or have enough knowledge of how things are going to move forward to suggest that any one of these technologies is the best technology for any one of our problems. So we're in a situation now where the community in general is looking at identifying the problems that are important to us and looking at modern systems, toy systems that have the attributes and share some of the features. And then we're seeing how these systems can be simulated on all of the different devices at once, where that's possible, where that's practical. And that type of activity is going to take us through the next few years. It's going to take us a lot of time. It's going to take access for teams of people to get onto each of these different architectures to explore. Oh, I should also mention as I'm sure you're all aware, we're currently sitting in the NISC era where none of these devices have error correction. Important steps are being taken, as I'll show later on, but these devices are generally noisy. They're not large. There's 10s, 20s qubits in the digital devices. The connectivity ranges from all-to-all connectivity, for instance, and as was demonstrated in 11 trapped ion systems, to, for instance, linear type of connectivity or ladder type connectivity, and there's also sort of specialty type interconnects that exist on some of the devices. So why do we think we can do things? So the important feature of nature that's really being exploited here is the fact that quantum mechanics works at all of the scales that we've probed so far. So the rules are the same, and so the rules of quantum mechanics and the rules of dynamics at very large scales is the same as at the very small scales, and also at the scale in the laboratory if we can control it. And so therefore, following the visionary discussions by Feynman, Benioff, Mann, and others, and also the understanding that one will not be able to simulate a more complex theory efficiently with a less complex theory, one expects that the dynamics of the quantum systems we're interested in for nuclear physics, ranging from length scales at 10 to the minus 15 and below meters to astrophysical, can all be mapped onto quantum systems and quantum computers and quantum simulators at that are the scale of the laboratory. And so the challenge for us, one of the big challenges facing us, is given what the problems and the systems that we have that are important for nuclear physics, is how do we do that mapping? And so this is at its very earliest days now. There's been good progress, but this is a task that is just beginning for us. But it's fully expected, because of this, if you like, this scale invariance of the rules of quantum mechanics, it's fully expected that this can be done. So as I mentioned earlier, our community through a community-wide effort, understands well its classical computing resource needs through the exascale. And so one of the challenges that we face in using quantum computers and quantum simulation is to understand which parts of the problem can be simulated efficiently classically. So and to separate the problem in such a way that the pieces that can be simulated efficiently on a classical device are simulated on a classical device. The quantum device, the quantum commodity is scarce, and so is to be used sparingly. And unfortunately, entanglement's not a sufficient discriminator to determine this partitioning. There's systems that are entangled that can be simulated classically efficiently, and so the challenge here is a little bit deeper than that. We need to take our problems and dissect them really down to the level of understanding which of the components we can, where is the dividing line, which parts do we have to push onto a quantum processor, which parts can be done on a classical processor, and understand how to do that partition, how to perform the computations in parallel, and then how to bring them back together and join them up to get to the physics observable that we're interested in. So another one of the challenges that the community is working on and starting to embark on is to start dissecting our problems. And unfortunately, you know, as this is just starting, we haven't completed the task, so we don't know for any of our problems how we're going to actually do this partition ultimately. But progress is being made, at least on the small systems, to try and understand this part. So the takeaway from this slide, if you like, is that we have to know our problems. And so I have just 3 or 4 slides here on probably highlighting and outlining things that you already know. And that is, where do we expect to find quantum advantages, or where do we think we'll absolutely need quantum computing and quantum simulation to be able to accomplish the goals of nuclear physics? And having said that, I should also indicate that it's not just for nuclear physics. The commonalities here for the requirements typically transcend the boundaries of the science domains. So the attributes of our problems that require quantum computing have analogs in high-energy physics and in condensed matter and other areas. So one of the nice demonstrations that's been known for 20 years now, developed in the quantum information science community, is the fact that real-time dynamics of quantum systems can be performed efficiently on quantum devices. It's in the BQP complexity class. Excuse me, this was shown by Seth Lloyd. And so in that instance, and sorry, not in that instance, but for these situations, on classical computing side, real-time dynamics is not tractable at any level of precision for systems at scale. And so quantum simulation then offers us the opportunity to perform real-time dynamical evolutions of lattice quantum field theories, effective field theories, phenomenological models, neutrino systems, any of the systems that are important to us, including the complex, things that are almost dreams for us, is that the highly inelastic processes and fragmentation. Of course, I mean, it's easy to say this. It's not yet been demonstrated at any significant level that, in fact, this can be done in the near term. This is something that is being worked on, and is, the progress is good. But in order to, for instance, to perform time evolution of system with a significant amount of inelasticities and fragmentation, we have to understand how to detect it, how to measure it, and how to quantify errors and so forth. Another area that's very challenging classically and inefficient on classical devices and beyond exascale compute resources is for finite density systems and high density systems. So as we're aware, there's been an enormous amount of classical computing resources put into establishing the QCD phase diagram. It's well mapped out at 0 baryon density. There's a sign problem that exists in the Euclidean path integral at non-zero baryon number density. And so a number of techniques, algorithmic techniques and formal techniques have been developed in an effort to try and get around the sign problem. Of course, none of them do, but the progress, at least there's a series expansion and other techniques that exist that we can move towards this. And so there's successful programs in Lattice QCD and elsewhere that's allowed us to map out within regions of where, for instance, the critical point may not be, is not, but this does not extend by any means throughout the whole phase diagram, and still an active area of investigation. Now, it's on the quantum simulation side, because we're doing real-time dynamics, there is no, one doesn't encounter the sign problem, in particular in the Hamiltonian formulation, which is what's going to be used, which is being used. There is no sign problem. On the other hand, we haven't shown, there is no proof that systems that we have, even at finite chemical potential, are efficient on a quantum device. So while we expect naively that the difficulties that we face, for instance, in QCD at finite density aren't present, certainly the problems in Euclidean space aren't present, but but there's no proof yet that in fact this is going to be efficient even for a quantum simulator, and it may not be at asymptotic scales. However, this is a tool that will allow us to conquer some of the sign problems that we have, if not all of them. So this is a slide which is a combination of the previous two. So, for instance, we have systems that are in nuclear physics that are non-equilibrium, finite density, and for instance, neutrino dynamics in a supernova is a combination of all of the above. And so one of the projects, or a number of the projects in our community, is to look, for instance, at neutrino evolution, where, with the time evolution of the entangled wave functions, interacting, for instance, with in a bath. Complicated calculations, but the quantum simulation is a new tool that will allow us, hopefully, to make good progress on problems, this problem and problems such as this, not encountering the problems encountered in classical computing. And so there's a number of different avenues that are being explored, for instance, electroweak processes on nucleons and nuclei, for instance, relevant for the determining neutrino properties in the Dune experiment, where one has a nucleus that's interacting with energy and momentum transfers, a few hundred MeV, which means there's no big parameter and there's no small parameter in the kinematics, which makes it complicated. A direct real-time evolution of such a system is being explored, and progress is very encouraging. And the quantum simulation offers an opportunity to potentially solve that problem and more. And of course, at the heart of nuclear physics is the study of the structure of nuclei. And again, many of you on this meeting are involved in such calculations with large-scale high-performance computing, and know the challenges here better than I do. The quantum simulation offers the potential of exponentially large Hilbert spaces, and if one can maintain and perform operations in these Hilbert spaces, then this is naturally far more efficient for dealing with these n-body problems than classical computing. And many of you actually on this call could speak about this far better than I can. So I get involved through Oak Ridge, which with the vision of David Dean, one of the members of our community, had moved along this direction early, and the team here, in the upper here it is. The cloud computing of atomic nucleus was truly one of those moments where I saw this paper and I just smiled, because you realize that something significant just happened, right? And what was contained in this paper was a calculation using low energy effective field theory in a low dimensional space, tuned to experiment that used a quantum computer to reproduce the binding edge of the deuteron. It reproduced it with, a 1% error, which means it didn't change what we understood about the deuteron at all. But it showed that quantum simulation and quantum computing had just reached the threshold where it's important for us to now pay attention to it. It demonstrated that the algorithms and the devices were capable of getting us into the situation where we could start down the path. So I really like this paper. It really changed my thinking. This paper and another one on the Schwinger model from 2016 out of Innsbruck really changed my thinking and redirected the community. This was one of the pioneering works. So then Seattle became involved in this, working with Oak Ridge, and we, for instance, and Thomas here was certainly was also front and center here. So we were able to then use, for instance, a device that Oak Ridge was developing, a quantum frequency processor with standard telecommunication equipment to try and see what could be done here for nuclear physics. And so Thomas looked at the nuclear structure of the deuteron helium-3, helium-4, using VQE algorithm to find the ground state, and of course was able to reproduce on this device the values that were actually input, which was with good error bars, which was very encouraging. And we're able to do a sort of a primitive, very first early match between the lattice Schwinger model, which is the one-dimensional analog, if you like, of lattice QCD, with a phenomenological effective one-dimensional lattice pi-less effective field theory. But in particular, in the Schwinger model, to look at the potential between two external charges as a function of separation, which is effectively the prototypical first calculation one does in a lattice QCD calculation to obtain the string tension as one of the means of setting the scale. So this time period, which is not long ago. I mean, it seems like yesterday, but it was now like 3 years ago. Really redirected my thinking and many in the community, and demonstrated that this was the path forward, a path forward. So we were recently asked to write an article for a journal, a sort of an overview article, and so this meant standing back and really understanding what are the essentials for the near term, to really understand for us to understand as to where we should be going, given the fact that we have to explore everything at the moment. And so one of the areas that came up was complexity, and this is one in the quantum information science community. This has been driving a lot of the analysis of problems, and so as you know, we have the whole concept and the framework out of computer science on complexity classes, and this really dictates that for a general problem, how do the resources scale as you increase the size of the system that you're simulating. And so on the classical side, if something is sitting in the complexity class P, what that means is as you increase the problem size, then the classical computing resources increase polynomially with system size. And so that's great. These are the problems that we can solve efficiently. NP means that you can, if you're given a solution to the problem, you can verify that it's a solution in polynomial time. And then you have, this is a picture, I should say, from Scott Aronson, Scientific American. And then the BQP, which is the problems which, with bounded error problems that scale with polynomial quantum resources, lie outside P, or expected to lie outside P. And so one of the things, another one of the things, and I keep saying one of the things because there's many, the problems that we have, at least in lattice QCD and in quantum many-body systems, we're always finding solutions with a bounded error. Right? We've never had, and we will never have infinite compute resources. So we're computing the results we're interested in, for instance, the location of the ground state or the mass of the nucleon, for instance, in lattice QCD with a given error. This error is driven by largely by how it's going to impact the experiment and complement other measurements and other calculations in such a way to move the field forward. So there's always targets on our computations, precision targets. And so this has actually allowed us to do a lot. If we were really focused on doing infinitely precise calculations, we would have actually probably not accomplished much. Because I think formally, essentially all of our problems are outside of the complexity class where you can actually do them efficiently on classical computers. On the quantum side of things, which is here on the right-hand side, there's been there's some understanding of some of the problems as where they lie. And so, for instance, finding the ground state of a k-local Hamiltonian, and this is including k equals 2, which would include the pi-less effective field theory. This is QMA complete, and this lies outside of the complexity class that can be simulated efficiently on a quantum device. And so we will not. So in general, for an arbitrary type of Hamiltonian with even two-body interactions, this does not scale well with regard to quantum computing resources. On the other hand, interacting scalar field theory, lambda phi 4, sits in BQP complete. That means it's efficiently simulatable on a quantum device. And it also means that all of the problems in BQP can be mapped with polynomial resources onto the interacting scalar field theory. So this is one of the reasons why speaking for myself, why I and others, of course, in the field, including those that are working on this, the Jordan Lee Prescott, this is why it's worth spending effort here, because once we can understand how to simulate this theory, including coupling to external sources, then in fact, you've understood how to solve all of the problems here. You just need to know how to map. So this part here is particularly troubling, but as I'll say, it really shouldn't be. So should complexity be a limitation? And the conclusion is not until it is. We wouldn't have made any progress classical computing really if we'd have worried about the complexity classes. And we've made good progress on the problems that we're interested in. So firstly, we're not dealing with asymptotic resources. We're always dealing with finite problem sizes. And so for instance, if one has something that scales with polynomial to the 10th power, then this is far worse scaling than something that's exponentially scaling until you get to about x of 9,000. And so this is certainly, this has been highlighted over the last several years by the quantum chemists looking at quantum simulations for chemistry, and that is you need to know the coefficients of the polynomial terms and the coefficients here of the exponential terms in order to understand just exactly how your resource requirements are going to scale. So the complexity class indicates the worst case scenario, and there's certainly values of coupling constants in the same Hamiltonian that are in different complexity classes. I take that back. That was not precise, but there's certain values of coupling constants in those Hamiltonians that allow for efficient simulation. And so it's this B in BQP that gives us the latitude that in fact we need, because there's an error. So we can change the theory. We can develop perturbation theory. We can identify expansions and identify what is leading order and what's subleading order in a consistent way in order to make progress on problems that are formally in a complexity class that isn't BQP. And so one of the challenges that we have, in my view, is to understand on these challenging problems is what is the perturbative setup, what is the framework that allows us to use quantum devices to address our problems within a certain to obtain results within a certain level of precision. So if you look at what went on in the 20th century in high-energy physics, and this is just a very rough, non-representative discussion, but the 20th century in HEP it was twofold. One is really addressing short-distance physics, understanding what the fundamental Lagrangians were, and typically these were all developing effective field theories such as the standard model and QCD about trivial fixed points with perturbing around tensor product states, for instance, the parton model, and also developing non-perturbative techniques such as lattice QCD to be used with high-performance computing to in fact solve those problems in the infrared. And modeling in particle physics gave way to developing effective field theories, and typically, as I mentioned, the starting points, the leading orders were all separable. On the nuclear physics side of things, the story was not so different. In fact, the short distance repulsion of the nuclear force was causing severe non-convergence in many-body algorithms. And there was a point in the 1970s where people had thrown up their hands a little bit. But this field was remarkably reinvigorated by bringing in the technologies such as renormalization group and effective field theory from high-energy physics and some many-body algorithms from chemistry. And the use of the renormalization group softening the short distance part allowed the many-body techniques to converge. And in fact, that is roughly a 10,000-foot viewpoint as to why the field is so active and progress is advancing rapidly today. And again, modeling gave way to systematic expansions where one could quantify uncertainties reliably where possible. And so the 21st century is going to be analogous to this, except the challenge for going forward is how do you understand and include systematically quantum correlations and non-locality, both on the formal side of things and in algorithms, and also to be used directly in how do you set up quantum simulations for quantum computers. So, the circuitry is, we understand the circuitry for standing up, real wave functions, for instance. The question is how do you want to bring up, what entanglement do you want to bring up on the system? Which do you want to do on the classical computer? And what control and what evolution of the entanglement do you need to do to get to where you want to go? So what am I doing on time? Okay, I'll jump. So one of the things, and I'll just say a few words about this is, and this was, again, this is something that this community understands well, sign problems in classical simulations. There's a connection between fluctuations of entanglement introduced by Hamiltonian and emergent symmetries. And so typically what we found for this, in the two nucleon case at least, which was consistent with, for instance, the work of Dean Lee and others, is that systems with enhanced symmetry, emergent symmetries in this case, spin flavor, either issue 4 for 2 flavors or issue 16 for 3 flavors, correspond to Hamiltonian that doesn't change entanglement when the symmetry is exact. When the symmetry is approximate, then the fluctuations of entanglement are small. And the either at the symmetry point or near the symmetry point allows you to do numerical calculations classically, and then perturbatively, either perturbatively or through exact inclusion at some subsequent starting time, include the full dynamics. And this is the idea that I had in mind when I mentioned on the previous slide, is what is establishing the starting point. Where do you put the entanglement, and effectively in the simulations, when do you include the fluctuations of entanglement? So let me skip this on time. So the mappings. So the first thing that we have to understand is how do we map our problems onto a quantum register. And so one can be thinking about qubits, which is typically what one thinks about with digital simulations, qtrits, but generically as some discrete Hilbert space or sets of Hilbert spaces, including, for instance, in SRF cavities, as being developed at Livermore or Fermilab. And how do you arrange these Hilbert spaces in such a way to simulate efficiently the systems that you want to simulate? So one expects that if you're trying to evolve an in-body system for some interaction time t, and it's been shown, in fact, by Seth Lloyd, that you can simulate it with n degrees of freedom evolve through n time steps of length t. And it's also been shown that for fermions, this is, in fact, up to some polynomial factor how things scale. And it's also known, just like for biological systems, that d-dimensional systems are optimally simulated with d-dimensional systems. It makes a lot of sense. What this does mean that if we're trying to simulate, for instance, three-dimensional nuclear systems or three-dimensional lattice field theories, then one is going to need a quantum simulator where one can actually lay the problem out on a three-dimensional system. And so a two-dimensional system of qubits is not optimal for simulating three-dimensional quantum field theories or quantum systems. So this then pushes us immediately into the situation of having to be involved in the co-design so that the devices share the topology and the geometry of the problems we're actually trying to simulate. This is something that has been done in classical computing, of course, with the blue genes, but it's also important, and it's going to happen in the for quantum simulation also. So for quantum field theories, we know the degrees of freedom. So for scalar field theory, we have at each point in space-time, we have a real number. For QCD Yang-Mills, we have gauge fields. We know how to take these systems and lay them out onto grids. So for scalar field theory, there's a continuous real distribution of real number at each lattice site. For Yang-Mills, there's parallel transporters that take us between lattice sites, and on those lattice sites, the quarks can live in QCD. And so we need to understand how do we map our fields onto these finite dimensional Hilbert spaces, or in hybrid technologies with finite dimensional Hilbert spaces, potentially classical systems and the continuous quantum systems. There is no right answer that's been identified at the moment. So all of the different mappings are being explored. There's truncations that have to happen, obviously, with any computation, one has to truncate. So for lattice field theories, there's a truncation of the gauge fields that has to occur, and there's a number of ideas that have been outlined for doing this, and these are under investigation. Of course, one integrates out degrees of freedom always, and in the lattice one is integrating out the high momentum modes. And as a result, one's always simulating an effective Hamiltonian with high dimension operators suppressed by powers of the lattice spacing. With Hamiltonian simulation, unlike Lagrangian type simulation, there are conservation laws that have to be imposed by hand. And of course, because our devices are imperfect and without error correction, this is something that is very significant in present simulations, but will always continue to be significant. And that is, how do you catch the errors? How do you make sure charge is conserved? How do you understand your simulation? You're not spawning groups of clusters of color, for instance. And ultimately, of course, and we've done this with classical computing, is that we have to establish a complete quantification of uncertainties. And there's extra sources of error for quantum simulations that aren't there for classical simulation. As I mentioned, scalar field theory is the gold standard we have, and beautiful papers by Jordan Lee Preskel, where they showed for scalar field theory how to initialize two localized wave packets in the non-interacting theory, adiabatically move from the non-interacting theory to the interacting theory, release the wave packet, so they scatter, and then at late times, there's a distribution of particle fluxes that are then measured. And so there was a lot in that paper. They were able to track from beginning to end all sources of error. And so this theoretical analysis is under complete control theoretically. There's steps towards it, as I'll show, on initializing this on quantum devices to actually try and do the calculation and show how to do these things. There's certainly a number of elements that have to be put in place and advanced in order for this to be realized with control of errors. And let me say also, as I mentioned, so here's one example where you can consider multiple mappings of the scalar field. And so the basis, the field basis that was used by Jordan Lee Prescall has one body and two body interactions, for instance, and you can do gate counts and count the number of C naughts required in order to do one trotter step in the time evolution, and it scales with a very simple way. One can also think about, instead of mapping in the field basis, mapping in the basis of harmonic oscillators. And so this is, for instance, the n equals 0 level, n equals 1, n equals 2, and so on. And so that looks to have advantages, but it turns out when you actually look at it and understand how to do the time evolution, then in fact you have to worry then about interactions between the bodies up to the dimensionality of the number of qubits. And so the gate count actually, while starting off looking favorable at small numbers of qubits, 8 and 24 compared to 2 and 20, soon grows dramatically. And so this basis, as you get a scale, is something that scales poorly compared to the basis of the field basis of Jordan Lee Prescott. Let me skip that. So the Schwinger model shares many of the features of QCD. There's charge screening. There's flux tubes between charges. It has a spectrum that contains one body, two body, and even a bound three body system. And so this is a theory that's received a lot of attention. It's also, because it's one dimensional, it's also something that can be addressed on current devices. And while all of the calculations that have been done to date could be done on a classical computer, there is strong motivation to pursue this on quantum devices, because at some point you will just jump into the region where you can't do it on a classical computer and you can do it on a quantum device. And so the first work out of 2016 from Martinez group et al. In Innsbruck showed the popping of pairs, E plus E minus pairs, out of the vacuum as a function of time when you initially prepared the state in the trivial vacuum. The other thing is that makes this interesting to explore is it has non-trivial topological attributes to it. There's in fact a theta term, just like not just like, but analogous to the theta term in QCD. And so several groups have been exploring this both formally and also on the available quantum devices, trapped ion systems, superconducting qubits, and other optical systems. And so the most recent ones are from the Brookhaven-Stony Brook collaborations. One was if you initially prepared the system and then suddenly do a rapid change in theta, the topological term, and ask what is the current flowing in that system, then in fact you see time-dependent response to that rapid twist in theta, and you see as a function of theta what the currents are. And then also finding the ground state of the system. Classically, this is a sign problem. On a quantum device, it doesn't, and you see that you can efficiently, in fact, find the ground state without a degradation of uncertainties at any value of theta. So there's other interesting hardware that exists, particularly on the analog side. It's going to be the case that simulations on analog devices are going to be ahead of those in digital devices for the foreseeable future. And one of the ones I find particularly interesting is the quantum circuits. And so these are Josephson junctions combined with capacitors and so forth. And so there was a really nice talk by Ananda Roy recently, who's been heavily involved in this work, and they were able to set up these quantum circuits to simulate lattice Sine-Gordon and lattice conformal field theory. So lattice Sine-Gordon, of course, is the lattice version of the Schwinger model to first approximation. And the lattice conformal field theory, so this actually got a lot of implications for us to consider. So that's one of the reasons I find it interesting. If we're really looking, for instance, we have to include quantum electrodynamics and also quantum QCD, then at least in the ultraviolet, that's approaching conformal. So there's a lot to learn here, particularly in the structure of entanglement in the vacuum and in the low-lying excited states of the conformal field theory, and also of the Sine-Gordon equation. Another analog development that's ongoing is of SRF cavities. So this is occurring at Livermore and Fermilab. So these are high Q cavities with that can support multiple modes. So these are qubit systems, and they're driven with significant classical computing preprocessing to inject a signal that implements the time evolution operator, for instance. And so there's very encouraging results coming out that you can find online, in particular related to nuclear physics, looking at the behavior of the tensor force and spin systems. There's also developments on the AMO side that are truly remarkable in many ways. The number of ideas seems to be growing exponentially. One of them, of course, is in Rydberg atoms simulating link models, and so this is from a talk given by Federica Soracci, and so they are bringing up a link model on a Rydberg system, and so they have results for one-dimensional implementations, and they also have they are setting up to do two-dimensional QED. And so again, I certainly in this talk I can't do this justice, but this looks very promising, and the link models are certainly an important one of the important paths towards getting to QCD, for instance. The connection is not direct as it is in other implementations, but it's certainly possible that through renormalization group ideas, this will get us move us towards QCD. So let me just say a few words about QCD. I've got a few minutes. So this is something that I and others have been thinking about a lot. One of the implementations is the Kogut-Susskind Hamiltonian, which was written down in the 70s, where the Hamiltonian for Yang-Mills looks like a contribution from E squared and a contribution from B squared, in the basis where that's diagonal in E squared, then of course you have off diagonal elements induced by the magnetic operator. Sorry, and in sorry, and so what this means is that the setup is that between each of the sites in the lattice, there's a parallel transporter which gets turned into a state of issue 3 that connects this Hilbert space with this Hilbert space. And recently it was recognized by the Munich the group based in Munich, Banuels et al., and also us, that you could integrate out these spaces by gauge invariance and reduce it to having a dimensionality of the issue 3 representation at each of these sites, at each of the links. And so what this means is that then you have a Hilbert space sitting on each of the links that just defines the number of up indices and number of down indices on the issue 3 tensor. And this generalizes to issue n straightforwardly. And so the wave function for this system in general is then a series of amplitudes over the different issue 3 tensors. And so, for instance, if you just look at the subunit of one plaquette, then this link here is denoted by this ket. And because you can integrate over these objects, then you're just left with a ket that's P and Q. And so, for instance, this defines the Hilbert space of the P register. This defines the Hilbert space of the Q register. Now, if there was no other links around and you just had a single plaquette, then all 4 of these links are in the same representation of issue 3. But in general, that's not the case in 1D even, because these will be in different IREPs generally. But in 3 dimensions, then you have to worry about this in 3D. And I should add that there's been significant work by a number of groups, including the group at Maryland, Ray Chowdhury and Stryker, Davudi, on looking at different implementations and different bases beyond this one. And they all look promising, in fact. It was shown that to compute these issue n Clebsch-Gordons is actually efficient on a quantum device back in 2006 by Bacon, Chung, and Harrow. And so it's conceivable because one has constrained and controlled operations that has to apply to the quantum register to implement the action of the plaquette operator, that in fact all of this can be done efficiently. And I should have added that all of this work is building upon this pioneering paper by Burns and Yamamoto from 2006, and then work by Zohar, Sirac, and Resnick on how to implement. And so we performed a calculation on a single Yang-Mills link. So this is a single issue 3 plaquette with a basis that is truncated at some level, and looked at the time evolution of the single plaquette on the IBM quantum devices. And this worked nicely. We were able to move out roughly 2 to 3 complete time evolution periods. And of course, as you increase the number of trotter steps and reduced the systematic error, then the noise in the device grew. And so there was some sweet spot in order to find the optimum minimum uncertainty. And so this calculation has provided some benchmarks now to be compared with for instance, on trapped ion systems and any other device where people want to perform these calculations. So there's classical preprocessing for all of these things, and this was an eye-opener for us at some level, and that is, for instance, if you just want to implement a single plaquette operator in this 2-dimensional system, what are the classical computing resources you need to prepare to do that? And as a function of the cutoff of the dimensionality, it's the case that as you want to go to the continuum limit, as you reduce the lattice spacing, then this increases in this basis the dimension of the Hilbert space that you have to access. And so as you increase the cutoff, this corresponds to going to the continuum limit, and the number of matrix elements grows dramatically. So while if you just have two representations or 3, at 3 you're looking at 1,000 matrix elements. At 2, 4, 6, 8 corresponding to 3 up and 3 up and 3 down indices, you're looking at 24 million. So this grows to the basically lambda, the cutoff to the 12th power. But if you look at what you're trying to implement in the registers, then this is actually nice. You basically have this honeycomb type connectivity between the issue 3 IREPs that you need to be able to step through every time you act with the plaquette operator. And so you can arrange things in multiple ways, in particular as independent operations on P and Q registers, and then an entangled operation. There's implementations recently from Canada by Randy Lewis and Christine Mushik. They wrote 2 papers that were really very nice, implementing issue 2. One was on a D-wave and showed, in fact, using some of the methods developed in quantum chemistry by Google, doing time evolution on the D wave for this system, they also then perform computations on IBM devices to using VQE to find, in fact, the ground state of this SU2 chain, and also the mass of the meson in the system. And so you see the precision is good, and there's clear discrimination between the ground state and the first excited state. With the algorithm they're using, they're able to, this is a very nice calculation. There's a lot of value in looking at model systems on the way to simulating quantum field theories. Particular spin systems are of remarkable value for in their own right, but also developing technique and understanding for the things we want to do. And so this was work by Ashley Milstead and collaborators out of Caltech and Google, where they're looking at this spin system. And in particular, there's turn off this coupling, and you prepare two domain walls, and then you scatter these domain walls off each other and ask what happens. So when this is zero, in fact, there is no ballistic generation of particles. There are no inelasticities. But what you're seeing here is the entanglement entropy as a function of time, and each of these crossings corresponds to a crossing of the domain wall. And you see evolution of the entanglement within that system between the walls. So this is as you partition at that point in the spin chain. On the other hand, when you turn on the coupling constant lambda, then in fact, as these collide, you can get the ballistic production of excitations in the system corresponding, at least in QCD, to the production of, high energy particles or jets or inelasticities. And so one here can use these systems to understand basic things about the entanglement, but also understand how to build detectors into simulations to try and do better detection of particles, which is going to be very necessary in simulations for instance, in high energy physics. Okay, I need to wrap up. So I get to skip a couple of things. Let me make one comment on the way to ending. So there's been a lot of developments. There's ongoing developments in new ideas, in algorithms and hardware and co-design. And so the Maryland group is one of the areas where co-design is really thriving. And as one example here, they were at a recently show. So this was Andrade, Davudi, Grass, Havizi, Pagano, and Sif. And so they were able to show how to engineer a three-body interaction on trapped ion systems. And so in the same way as you can build a Morrell-Sorensen gate through expanding exponentials and the appropriate exponentials corresponding to the application of lasers, you can engineer a three-body interaction in the same way with different sets of lasers. So they actually now understand and are building systems that can efficiently introduce a three-body interaction or three-spin Hamiltonian. So that's really exciting, particularly for nuclear physics, where we have three-body forces and potentially four-body forces that we want to also include. Yeah. So one of the things that was exciting to me earlier in the year was the progress towards error correction, something that I did not recognize was so near to us. There was papers by a couple of companies, one Honeywell and one Google. In the Google paper, they showed that, in fact, with the repetition code, they saw, using the Sycamore chip, the exponential suppression of errors as a function of system size defining the logical qubit, which is really exciting. And then they were also able to demonstrate they could actually detect errors in a surface code. And the Honeywell, they were able to establish some of the elements needed to have, for a color code, it was a 713 Steen code, but they were able to establish on their device the basic building blocks for implementing it. And just one last comment, a paper that Natalie Clough and I just put out last week or the week before, was using the ideas that we use every day in nuclear physics, and it was based on effective field theory thinking to put an idea out there with regard to hierarchical error correction. So so typically our problems have hierarchies in them. That's why effective field theories work. And it turns out that at least in the simple cases, one can map these hierarchies onto a hierarchy on the quantum register. And what that means is that some of the qubits will contribute significantly to particular amplitudes of interest, and others will only have small contributions. And so what that means is that when you're worried about error correction on such a device, you just have to error correct well, the qubit with the large amplitude, and you don't have to really worry about error correction too much on the qubits that have small contributions. And so then you can sort of dynamically rearrange your physical qubits into logical qubits to optimize your calculation with regard to uncertainty and errors. And we found that you could reduce the number of qubit requirements by about 60% by doing this. So let me finish. So basically, quantum computing for nuclear physics is here at the beginning. So what that means is we're just embarking down a path. It's going to be a long path, but it's clearly important for the future of nuclear physics. It's going to allow us to address problems that we can't address any other way. We just have to now deliberately and systematically establish the path towards meeting that objective. So this is going to impact what we do for quantum field theories, non-equilibrium dynamics, inelastic processes, and so forth. Co-design is clearly critical in advancing this field efficiently and reaching our science goals in the shortest possible time. This requires developments in algorithms, mappings, devices, and really understanding our problems and how to slice and dice our problems to best utilize the available resources. And at the heart of it is the new laws that are being used. So it's entanglement and coherence are the new attributes in quantum that we don't have in classical computing. So we have to figure out how to optimally implement and understand these. So thanks very much.
Thank you, Martin, for a very nice and complete presentation. So I guess we have time for a few questions. So, feel free to unmute yourself and ask the question if you want directly. In the meantime, I have a question. So Martin, you explained, very nicely, several examples of implementations, right, of simulations of dynamics, for instance, right, on existing technologies. So what is the main bottleneck right now? So is it in the number of qubits? Is it in the number of unitaries that you can perform before the error becomes too big? Preparation of the initial state?
So there's a number of there's bottlenecks everywhere you look, in some sense. Coherence time is a large one. So how many gates can you apply for what and have the device remain coherent and quantum? That's a big one. But on the other hand, if you gave me a device with 100 qubits and asked me to use it efficiently, I couldn't do it. Right? Every time you sort of jump an order of magnitude, or in classical computing, it's the same way. Every time you increase the device by a lot or add a new feature, there's lead time required in order to figure out how to use it optimally and do it. So at the moment, I couldn't use a 100 qubit system to simulate anything. Give me enough time, and great collaborators, then of course it can be done. But there's a sort of a knowledge bottleneck that exists. Understanding how to slice our problems up, another one. We're still really making that progress, as I mentioned. The devices themselves can't sustain what we want to do. So you saw how far you can go in one plaquette. If you wanted to do that now in a local basis on one plaquette, you can't get very far. So most of the devices won't even sustain the devices that are available to us won't sustain really one plaquette, right? So that's a severe limitation, right? But so, you know, basically, as far as QCD is concerned, if we were given a device with, say, you know, 40 qubits that were coherent for an extended period of time, then we could begin to learn how to really implement multi-plaquette systems. So we're sort of at this point where the device is now limiting us from actually developing the better understanding to use the device at that scale. So this is where simulators come in, of course, and to get on a classical simulator to do something at the level of 50 qubits is, of course, critical.
Great, thank you. Any other question?
Well, I have a question about similar lines, because I mean, I mean, would you agree with me that if you are trying to find quantum supremacy in any of the questions that you can ask to your system, it's better to look at dynamics, because it's known that, you know, the calculation of correlators is BQP. It doesn't matter, it's two, you know, it's two body or three body or four body. Therefore, if you are going to look for quantum supremacy in any of the things, one should start in looking at any dynamical problem where you can exploit 100 qubits or 150 qubits and not looking at the phase diagram. So I think that this is the wrong strategy.
Yeah, so I'm very fond of time evolution for the reason that it is BQP, for the reasons you say. It's exactly right. You know, and the challenges, at least the ones, so there's really two main things, say, for in-lattice QCD that are challenging. One is dynamics and one is finite density, right? And finite density needs to be explored. I don't know, we don't yet have an understanding of why it's more challenging, but the time evolution, as you correctly say, is if you can prepare the state, the initial state that you're interested in, then you can do the time evolution, right? So the time evolution, I agree with what you said completely, but it's preparing the initial state to be something that you can then compare with experimental as relevant. There's the challenge for this.
Okay, but then I will come to you. How is that experimentalists prepare the initial state? Do they prepare the ground state of QCD?
They do. They have a proton.
All right, but I mean,
they have a proton beam.
But
so nature's prepared it for them.
Come on.
No, I mean, if you have a proton beam, that's an eigenstate of QCD that's been prepared by nature, right? And so that is far beyond what we can do on a quantum device today. So nature's intervened.
You would argue that nature prepared, you know, ground states more efficiently than the way a quantum computer prepares a ground state? Is that the case?
No. My position is nature's prepared the ground state of QCD better than I can prepare the ground state of QCD.
Okay. That is fine. But but philosophically, it's an important question. I mean, it's not an irrelevant question. So if you assume that nature prepares ground states better than we do, then we have to start thinking, you know, in a creative manner. If, on the contrary, that's not the case, so why should you be worried about?
Well, so, you know, the fact that you can isolate a proton and play with it in the lab as much as you want, and you can also prepare a beam of them, that gives the experimentalists a massive advantage over us starting with a system of qubits and trying to actually prepare that same state, that lattice state. And, you know, in principle, it shouldn't, you know, in principle, I think in the big picture, you would think that nature and a quantum device will be able to do the same thing ultimately. But right now, nature is well ahead of us in preparing the ground state of QCD.
Okay. I mean, I could say that if that is true, quantum mechanics is wrong.
Yeah, I'm not going to say that.
Well, I mean, maybe I'm wrong, okay? But
this is not, and I wasn't trying to trivialize what you said. You know, if you can show that, then that's really interesting. You know, so for example, one of the things that's a little bit more that are along these lines is that, we don't, as far as classical calculations go, we don't know how to simulate chiral gauge theories efficiently on a classical computer, right? We can do QCD vector theories, but we can't do chiral gauge theories. And the hope is, at least on a quantum device, one will be able to do a chiral gauge theory. But so far, nobody's shown how to do that. And if it can't be done, then that's one of similar along the lines of what you're saying. That would be an interesting thing to understand. In a quantum simulation, can you do a chiral gauge theory? Because that would then say nature and quantum simulation are a little bit different. But it would, to say that quantum mechanics is wrong or quantum field theory is wrong, we got a long way to go to even think about that, I think.
Oh, I believe you, but what I'm saying is that there is some philosophy. I mean, the question is how you falsify these things. That is the question, okay?
Yeah.
And that's the reason why I'm saying, well, we know perfectly well that mathematically you can prove that the calculation of any correlation function, okay, time-dependent correlation function is BQP.
Yeah.
That is proof, okay,
Yeah.
with quantum mechanics. So I can prepare initial state in polynomial time, a simple state, and, should work. Okay, so can one design an experiment with which you can compare, a real experiment that, in some way shows proof of disprove that statement, okay, that you can reach, and, perhaps in the experiment nature is more efficient.
Yeah.
It's more efficient nature. I don't know. But is there any way of falsifying that thing? Because I think that there is an important point there for simulation physics.
Yeah. No, I agree. It's an important point. I don't really have anything useful to say, really.
It's food for thought.
Yeah. No, I agree with you. Yeah.
Probably it's time to wrap up. So thank you very much, Martin, again, for a very nice presentation. And thank you everyone for joining. See you in the next presentation.
Well, thanks very much for the invitation again.
Thank you, Martin.
See you, Christian.